Since you're all used to this, there's a big flash up right now that says, caution, this meeting is being recorded. Continue, leave. Continuing. So, at last we left our faithful hero kids. We were in Thermostoich, and we said that heat could be a reactant or heat could be a product. And the big review is simply that positive delta H, endo, and heat is going to be a reactant. Negative delta H, exo, and heat is going to be a product. And this helps me keep things straight. Realize we haven't done much with reactions yet, but a reaction is merely happening inside of a vessel. So we can't just add something to one side of a reaction. We have to add it to the entire reaction vessel. So that's not going to get too bad with these. It's calculate the heat in kilojoules. We like it when they ask us for the units, tell us the units they want. And it's going to be associated with 155 grams of NH3. So basically, NH3 is my known and energy is my unknown. So if that's the case, when in doubt, turn things into no. MCAT is backup plan B. When in doubt, turn things into moles. Yeah. No. When in doubt, convert to moles. That's the only when in doubt until we get to pChem. Okay. So 155 grams, NH3, zip, think, 17 grams per mole. Mazel tov. I'm going to finish the problem though. And that's at a negative 906 kilojoules per 4 moles. I don't know if I can. I don't know how. Press the green button on the left.
It is not in the trash.
Green button.
Above that.
Yes.
Okay, we got
Thank you.
negative 2065.14.
I'm gonna check your work. Thanks.
With your prediction.
Yeah, it's a lot more accurate. Than your.
This Casio 5X1 PDF plus. I forgot we're recording.
Did you say negative 2065?
Yeah.
I like it. Kind of. Kind of. Hey, Skipper.
So we're converting to moles and then what are we doing?
Oh, significant figures.
We multiply the.
So yeah, convert, take your mass, convert it to moles. Then use the energy given in the problem, kilojoules per moles, and that's per 4 moles here. The problem we did yesterday was per 1 mole. So now we have one with a coefficient, which is per 4 moles. 3 sig figs, 2070.
Wait, why are you multiplying by delta H?
So is the delta H reaction just negative 906 or the 906 per mole?
It's 906, and it's a great question. It's 906 per 4 moles of NH3, per 5 moles of O2, per 4 moles of NO, and per 6 moles of H2O. It's per moles of each substance. So it's relative to each individual reactant or product.
Okay. On the test, will you care what the correct number of sig figs?
Plus or minus 1. I mean, get me really, really close. Yeah. If you write out, 11 decimal points, I think that's kind of bad. Okay. No, remember, this is thermo. No individual problem is bad, but there's a lot of different types of them. This one is a broad, shallow topic. We're not going deep, but it is broad. Okay, so now it is, here's your heat. Whoops. One 1.5, 10 to the third kilojoules of heat. What mass of CO2 is going to be produced? So that's my unknown. And 1.5, that Q or H.
Oh, this is the
Remember, we're dealing with Q. Q is, leave Q off for E equals Q plus W's or bombs. But for the rest of it, let it be H. So let's start with our energy. So we're just going to start with energy. From energy, we're going to go to moles. And from moles, we're going to go to grams. One mole of C4H10. Whoops. Kidding. We don't know what? The what? Right. Yeah, we have two problems to do here. Oops. C4H10. And that's negative 2658. And 58 grams of C4H10. I'm gonna I don't like it. So how do we fix it without cheating? Because normally we just would say you can't have negative mass and we would just cheat. But let's fix it the right way. Fix the problem. Not the problem, but the solution. Not the constant, but it produced 1.5.
That's exothermic.
Yes,
That's negative.
yes.
Oh, negative is negative.
So negative divided by negative. Now you can have positive grams.
So where'd you put the negative? On what?
On the 1.5, because it was producing that much energy. So it gave off, released, produced, released, liberated. It sometimes says liberated this much energy. That's a weird word. We only think of that in terms of like, Italy, but Okay, now what about part B?
Oh, you can do Stokes speed and you can do the Stoic. You do the Stoic rate.
Just do the stoic thingy. Where do we want to start?
You start by converting a mole. And then you do the coefficient.
Okay.
So you still use that 1.5.
Yes,
Because that's just for everything.
right. Because that was given to me in the problem. I could start with 32.7, but I think that would lead me to a mistake. And I don't want double jeopardy if I get it wrong. So in this case, it's 4 moles of CO2 and 44 grams. You got it?
Yeah.
Because I'm probably going to get spinny ball of death.
99.2.
I don't believe you. Yeah, check this one, Kyle.
I mean, it's getting better.
That is not true.
No, it's just writing this down. No, this is fun.
I can't even punch it in. 1.5. E3 times 4 times 44 divided by 2658. What'd you get, Arian?
99. I got 99.3.
I got 99.3.
Wow, yours is so bad. Are you? What day of what? No. Oh, I did a more.
Well, let's just agree 2 sig figs and we'll be happy there.
Wait, why 2?
Because of the 1.5. Technically, this should be 33.
Oh, you're right.
It's what they gave us in the problem. They only gave us 1.5, but nobody does.
The figs aren't supposed to.
What we like is it does give us the same answer. So we don't sit there and go, well, I got 99.322799091. I take it back. There is a prof at NYU who really likes sig figs way too much. Yeah. Yeah.
When do we use delta H equals negative P delta V?
When we want to calculate. Wait, say that again. When you
Like
use,
something equals delta negative P delta V.
that's energy.
Wait, it's
E-
not work.
No, that's work.
That's work. W equals negative P delta V. Let's, and we'll do this. When we get to the end of all this stuff, we're going to sort out, okay, here's this equation. We'd use that with this kind of problem, this kind of problem, this kind of problem. Here's another equation. Use that with this and this. Yeah. That'll help.
You got this, Emily. I know you slept last night. I actually did. Right.
Really? Because amazingly, Arian came in and hasn't given us a sleep update.
Arian slept so well. He slept like a log for like 9 hours.
I can like just hit one position and I'm out.
Yeah, no, not me. I fell down on my bed and I just ate a log.
There you go. So kids, we take some sodium hydroxide pellets. Boom. Throw them into some water. Here's what the reaction looks like.
Pellets.
Pellets. It doesn't come, it comes in flake form. It also comes in pellet form. It doesn't come granular.
Is it not like the one
Like fish
so you make
food? Fish? Oh, I know.
Yes, yes, like fish food. It's a pellet.
I know, I forgot it. It's just talking about like the pellet.
The important part isn't the pellet, kids. The important part is that pellets are solid, and when you throw it in water, it's going to dissolve. When it does so, it is going to liberate 43 kilojoules. Okay. So A, B, or C, is the beaker hot or cold?
hot.
Good answer. Exo or endo?
Okay.
Fantastic. Calculate the heat when 14 grams.
79.35.
That was unnecessary.
That was an epic fail.
Could be off by like
Start with 14 grams.
NaOH. What do you call that?
Sodium hydroxide.
Oh, it was in the cross. Honey, give me the periodic table.
Oh, I searched it out, bro.
Whatever you do, put them back.
Yes, I will put that. I always put back.
That's what Arian said too.
No, but he doesn't put that.
He said he does.
what I.
Arian is a liar.
Ouch.
Hey.
That's being recorded.
Wait, what?
What?
Putting back your calculator.
My calculator is very, very flat. It's a negative 15.1. Or it's negative 15 with kill bill. I mean, sig fig. Yeah, negative 15.
He is right.
I have a question.
So this is your heat of a reaction follow-up
So
stuff.
There's nothing over like Celsius and RAM. It's just kilojoules.
Correct.
No.
Calculate the heat because we took, it's a fair question. We've dealt so much with kilojoules or joules per gram degree Celsius or joules per mole Celsius. We've done all that. But in this case, with Thermostoich, we're giving you the amount. We're saying in 15 grams, 14 grams. So the grams are going to, they're going to cancel out your moles. That's the whole idea of Thermostoich. So it's calculate heat, just going to be kilojoules. Okay. All right. What's Megan doing?
She's doing her count.
What's on her screen?
It's a blank screen.
Really?
Yeah. There's like a wall.
Is all your homework done?
What?
What are you
Really?
doing?
How'd you finish it?
All right. Is your calc homework done? Okay. So here's a heat of reaction question. And this one's going to take a little bit different. We're going to walk through this. So I'm not throwing this one at you guys. This one's got a lot going on. Remember, this one has volume and concentrations again. And we did this yesterday where the prelim stuff that you need, and I know I'm off screen, but they learned this yesterday. They'll be fine. 1 molar is the same thing as saying 1 mole per liter. So when they give us a volume and a concentration, if you multiply volume times concentration, you'll get moles. Just watch out, your volume has to be in liters.
Oh, because milliliters per liters, liters times mole over liters.
Bingo. Lonnie, did you get that? Okay, so we've got our volumes and our concentrations. So that's going to get us to moles. We have density, which isn't 1 for a change. So we're going to have to use that before, maybe. It's got a mess of things going on. Okay, then we've got a temperature change. So here's our setup. You have a specific heat and a temperature change. Somewhere along the way, I'm going to have to do an MC delta T.
Yeah, we
You
love
know
that.
Okay.
that because you have the temperature.
Yeah.
Temperature change.
Now, it says calculate the heat of the reaction in joules. Yay, we like that. And then calculate it in kilojoules per mole. That's the fun part at the end. The first part should be pretty clean though. Okay. Calculate the heat of the reaction in joules. To get a heat of a reaction, heat of the reaction, RXN, is just MC delta T.
Yeah.
Yes, we like that. Great. What's our mass?
Our math is.
You have to
That's what
convert to
we're trying
milliliters.
to do.
Oh, you have to multiply the first
Yeah.
do it, right?
5 times 10 to the negative 3 moles per CaCO2.
Hey, Skip.
Yeah.
Why are we going to moles?
It's molar, molarity, right?
But
So
it's
51
not.
grams.
Or you want grams?
So that comes like mole is a gram.
I thought something.
One of the triplets said multiply by density.
That was, yeah.
I'm pretty sure it was Emily.
I think I can guess the other one.
That
Wait, we can Oh, wait, is this
Sorry.
being, I forgot this being recorded.
Gotta get the
Yo, you never heard that
1.05.
seal?
Where do you get 1.05? That's the density. 80, that's
Got the two added together. That's 30.
Okay, so kids, stick with me.
It is 0.555.
Thank you.
Correct.
Thank you.
Wait, 0.5. 80 times 1.05 is
Here, Kyan,
0.5.
let me help you. Kyan, it's 84. Okay, what, listen to your friend.
Hi, friend.
80 times 1.05 can't be a decimal.
Where did you get 80 million?
you can just add the masses.
Oh, you add the
Yeah,
masses
the volume
together.
Sure you can.
They're about the solution.
Come on.
80 million.
If I give you 50 mils of that, 30 mils of it, what's your cost?
Okay.
The answer is yes. And the density of the solution was 1.05. This is going to go.
I got 80
as soon as you wake up.
You already did already. I'm kidding. Everyone in the other class, Aryan is in here. I just got
I think it's
Sunday. Oh.
No, I-
I've never gone to a
like, I know how to do it once in my life.
dangerous and not safe to stay farm.
And now when everyone's Thursday, oh my God.
First step is tough.
No.
Okay, so Emily, what do we do next?
See,
Oh, fine, we're 30. Do the same thing for 30.
30?
We combined. Oh, we combined it, just kidding. Combine the temperature.
What's the specific heat of the solution? 4.18.
Oh. Yeah.
oh, we got it.
And then the temperature.
T final is
24.8.
According to math, that's probably.
Don't do it yet.
So just be in joules, all right?
correct.
I don't trust your answer.
For the record, Ariam, we trust you. We just don't trust your Casio.
I cast.
So. Significant figures.
I'm gonna write a case from like that.
You got it wrong.
I know, but I'm getting plus or minus one. So give me that third sig fig, please.
Two. Yeah.
Why can't we affect moles first?
Because it wasn't thermostoich yet. Because all we wanted was the heat of solution.
Always.
And that was a good question. Why didn't we convert it to moles first? Because this one wasn't a thermostoich yet. This one is just what's the heat of the reaction. And so if it,
No, we'll explain it to us.
so heat of the reaction in joules, boom, we're good.
Now just kilojoules. Now
Okay.
we convert.
Now it wants heat of the reaction in kilojoules per mole. So I'm okay with you guys if you just go 0.702 kilojoules. Now we're not done. That's,
And how did you know that was gonna be a positive 7? You don't do like the endo axle, right?
no, because the temperature went up.
Oh,
Okay. So now, how do we get the moles?
Oh, we do, this is where we do the molarity thing. Moles per liter.
So now I have many problems with that. A, I have the talking stick. B, next holiday up is Thanksgiving.
But then why do the lights?
Because
They're
these
orange.
lights-
That's Thanksgiving.
They're
color.
Thanksgiving lights. It's candy corn.
Those like flashing lights are like gonna be like that.
Okay, so let's use,
You have to do this separately, right?
you have to do these separately. So I have 30 mils of AgNO3.
This is what this,
This is the part that you need to learn.
I got this,
No, you don't.
but I.
I had 30 mils of AgNO3.
Oh. So you just converted automatically.
Yep. That concentration is 0.2 molar.
So that's what capital N means.
Oh, that's.
How do you know it's 0.2 molar per liter, not
That's,
milliliter?
that's divided.
Because that's the
Capital N.
definition of what molarity is.
Oh,
Molarity
yeah.
is moles per liter. So that's moles of AgNO3. And for every 1 mole, for every 2 moles of AgNO3, whoops,
0.01.
That's your unknown. Yeah, unknown. Wait, what is that? I think
That's your solution.
and you just picked that as the solution? You
Yep.
could've done that wrong.
Yeah.
Oh, we're using like the.
Solution, not one of the three.
he's probably going to explain it.
Just, you know, stay attentive.
I understand.
I need white out. This is not.
You need what?
I converted to pencil a long time ago now. I learned my lesson. in
Oh,
pencil.
yeah. Who would still be writing in pen that isn't a Frixon? Oh, good
I
heavens.
only write in
Wait, so
pencil
what was the point of the
Sharpies.
first part? What was the
I
point
guess
of
you're
the
referring to-
0.702?
Wait, Bob, what did you say? Quicksand?
Frixon.
What was that?
They're the erasable pens.
Oh.
That he told us
I
about.
thought that was like the-
Oh, no.
What's that other thing you called it? The one- the thing we searched up, but it was like.
We kind of forgot her lunchbox again. I brought them.
what do you call it?
Wait, what? Oh.
I'm confused.
I know you are. I'm going to show you the solution and then explain it.
Okay. Oh, is this the like
I get.
the one you picked the one that's smaller?
This is a limiting reagent question, kids.
We already did this part.
We did this part, yes. All I'm doing here is using solution, which we haven't done, but we taught you how to get solution to moles. And then we found, yes.
This is,
This-
this is called thermostoich.
Okay, whatever.
And so we're finding out which one's going to produce the lesser amount of CaNO3 and that's how many moles are going to be consumed.
And now you just put the 0.702 over the final row. To get the protein whole, right?
Oh,
Calcium.
That gives you
chloride,
a good answer.
I think I get it.
A
So
roughness.
AgNO3 limits use the AgNO3 moles.
And then that'll show you the reaction.
That's going to give me the heat of the reaction in kilojoules per mole. Okay, Michael, how many moles of AgNO3 or how can I find out the moles of AgNO3?
You can do that. We start out with. There you go.
The 0.030 liters,
And then don't you multiply that by the molarity?
multiply it by the molarity, 0.2. Good answer, Michael. So 0.006 moles of AgNO3. That's the moles that are consumed. Moles are limiting. So delta H here is going to be the 0.702 kilojoules divided by the 0.006 moles,
117.
117. I like it.
Why is it 0.005 moles crossed out?
Because that was a high mark.
So go back to stoichiometry. We produced a product here. We produced the same product. We produced the CaNO3. And
Oh, and the
we
reason
chose the
for-
smaller answer because that's the one that tells me the limiting.
So you do like that, the thermostoich.
I don't fail.
whatever volt is,
Right.
And then
Oh.
when you want you to find the thermal, you use that.
All we've done in the bottom half of this problem is find out the limiting number of moles.
What is that 0.30 liters and
No,
then
wait,
multiply by?
how many frames on each?
This is how, so I have to do the two calculations here to figure out which one limits.
Yeah.
Then I've got to find out how many moles of the limiting reagent we actually used,
Maybe.
because all of the limiting reagent got consumed.
Okay. But why, I don't get why you need to find out. Why do you multiply by 0.2?
You don't get why we use the limiting?
So why would we need to find that? If we, and I get up until 0.702 kilograms. And like, I don't get why we have to find that.
Okay. It's fair. AGs. Doesn't matter. So if we start out with 30 mils of 0.2 molar, and we start out with 50 mils, what's my concentration of the CaCl2? 0.1.
0.1.
So 0.006 moles, 0.005 moles. All I did was get it into moles. This is before.
Okay.
This is initial. After the reaction has occurred, all of that got consumed. We made 0.003 moles of this. How much CaCl2 is left after the reactions occurred? This is chapter 2, kids.
I know.
Three.
I don't like stoic.
No.
0.00.
All of the AgNO3 got used up. This is the how much excess remains.
0.002.
How do you do that?
You subtract.
Oh, that's it.
So here's what he did. He took 0.0, got it? 0.006 moles of AgNO3. 1 CaCl2. This is really shoddy work.
Shoddy.
What is that?
Shoddy.
This is the 1/2 ratio. So 0.003 moles of CaCl2 got used. We started with 0.005. We're left with, we used 0.003. We're left with 0.002.
Mhm.
So the reason we have to, back to your original question, why do we have to use the AgNO3? Because it's the one that got used up. It's how many moles. Everybody's okay with, well, we produced 702 joules.
Yeah.
How many moles were used in that 702 joules?
Yeah.
And it was 0.003 moles. That's the hard part to see in this problem.
I'll just practice this. Okay, I'm good.
I'm with you.
I'll figure it out. All right.
We got a week. We'll be okay.
Yeah.
It'll be fine. It'll be fine. What's kind of.
He's just on a new tab. I don't know what to say.
That's Thermostoich. That's difficulty. That's DEFCON 9.
That's it? Like it won't get past that?
That it can't get harder than that. That is molarity and volume and limiting reagents and
This is
MC
it.
delta T's. That's putting a lot together.
I like MCAT.
Well, there's an MCAT at the beginning of it. Look, we knocked out the MCAT
We got
really
there.
fast. That was like, okay, here you go.
Would you see yourself putting a technical this part on the side?
Yes.
Love that.
Do you know why?
Because it's
Because we're like Highland, we can get the really hard problems right. It's the really easy problems that we like to mess up. Do you disagree? No,
Everybody hates arithmetic, right?
no,
Everybody hates arithmetic.
we like arithmetic.
What are you talking about? Use your calculator too. Just like me.
Well, that's part of arithmetic, isn't it?
Only the, no, I'm not doing anything. I'm just plugging it into this.
But you're having to plug it in.
Oh, so 1 + 1 is 2.
Yes. Yes, it is. Okay, that's Thermostoich. Yay, team. Let's talk Hess's law.
we're moving on right, like right along.
No, we're.
Every now and then. Now, only about a third of us understand the last problem that we just did. I'm sorry, all of us understand a third of the problem that we last did. But we've got a week. We'll sort it out. We'll do another one. Don't worry. We can come up with another one.
That's his love.
Waste time.
Finally,
Finally,
3 days late.
what does Hess's law tell us?
It tells us how to manipulate.
It's a way
It's like a coefficient.
to calculate delta H of a reaction using its parts.
Wait, which part? The system?
Yeah, different parts of the system. So you can manipulate chemical reactions using Hess's law. Basically, if a chemical equation is multiplied by some factor, multiply the heat. That's just like saying if I use twice as much stuff, I get twice as much energy. If I use half as much stuff, I get half as much energy. Okay. If we reverse a reaction, then reverse the delta H. So if I take energy out of water, it turns into ice. If I reverse that, put the same amount of energy back into the ice, it's going to melt. Reverse it. Reverse the sign. Energy in, energy out. Okay. And if here's the statement of it. A chemical equation is expressed as a sum, add them up, series of steps of the delta H's. So we play around. It's puzzles we were talking about yesterday. It's playing with the puzzle pieces, okay? And rearranging them. So here's our first example. It's algebraic in nature because according to Arian, everybody loves algebra. This is what's called
Hess's law.
my target equation. It's the target because that's what I'm trying to hit.
Yeah.
And it wants to know what's the heat of the reaction if for this one. So reverse and double it.
Yeah.
Right, because 2A plus B makes C, and that's got a positive 122. So if I reverse it, C goes to 2A plus B negative 122.
Pretty self-explanatory.
I mean, I'm not gonna lie, this really is a gift of teaching right here.
Wait, what? Don't you go?
So 2C to 4A plus 2B is negative 244.
That arrow.
So good, literally.
Oh, my arrow.
Okay, we can do this one. Yeah, this one's good. This we can do.
Okay.
Now let's
It
go
only
on.
took
Don't
us-
don't look at number 80 on the homework then.
It's just more equations though, like,
Right.
it's all the equations.
All right, now let's get to how we apply it and screw up Hess' fault.
It only
Okay.
took us 15 pages.
It only what?
Took us 15 pages to find something we can get.
Well, not really, because they were duplex, so it's 30 pages. I'm on 29 out of 42. Hess's law says the energy of reaction can be calculated by adding the energy of each step.
Yep.
Delta H is a state function, so heats can be added. That's the beauty of state functions, is you can just compile them. So here's my target. We want to find out the heat of the reaction for that, given the heat of the reaction for those. Bad news. States of matter matter
I get that.
because H2O as a gas has a different amount of energy than H2O as a liquid. 9 out of 10 times, it's not going to matter. It's just watch out when you got that H2O gas and liquid in equations, it can get icky. Okay?
Okay.
So we want 4NH3 as a reactant. So I'm looking at reaction number 2. Whoops. I want a double reaction 2. Does that look okay?
Yep.
Okay. Now, double bad news. These require a lot of writing. Not hard writing, but copying. So double reaction 2 and rewrite it. 4NH3. You understand why we're doubling it?
Yep.
To make that 2 match that 4. 6 N2Os, 8 N2s, 6 H2Os, and now double it and make it negative 2024. Wow, that's a good name for a game.
For what?
Graduation year.
Look at you guys.
No, 180, no.
What?
Negative 24, so that's like.
Yes,
If you were to calculate.
fair. Okay, so now let's see what else matches up from equation 1. The biggie is equation 1 has this N2O that's nowhere in my target. So I got to get rid of that. I've got 6 N2Os as reactants in equation number 2. So I need to get 6 N2Os as products. So this is going to take an R3. Show all work for credit. You show me R3. Tell me I'm reversing this equation and I'm multiplying it by 3. So now I have 3 O2s, 6 N2s, going to 6 N2Os. And now 164 negative becomes positive 164 times 3 becomes positive 492.
So why did you need to reverse it?
And like cross out the 2 and.
Because now look what cancels. Let me grab. No. So now the 6 N2Os cancel with the 6 N2Os. And now 6 of the N2s cancel and make that 2 N2s. Nothing else can cancel out. So now when you add them together, you're going to get 4
Oh.
NH3 plus 3 O2s makes 2 N2s plus 6 aquas And when you add negative 2024 plus 492, you get negative 1532 kilojoules.
That's not bad.
Not bad. They're puzzles. You rearrange, you flip and multiply and
Why, so you start with the bottom one because that was like the easiest.
start with the most complex molecule that I see. When I look at my target equation here, I've got two elements. Leave those to the end.
Okay.
Water's a very simple compound. Leave that to the end. But this NH3, that's only in one equation, and I got to start there. Let's start with the biggies. Then go back to your target and find out, look at that N2O. I got to get rid of that.
Yeah.
That's got to cancel. So find my place here to make that N2O cancel out. Work from most complex to simplest. You'll see fractional coefficients here. That's okay. They'll add up or you'll multiply or they'll disappear. Okay. Well, that was two equations. How do we make this harder, Neha? Four equations. I mean, if two was good, four is better.
Oh, great.
Oh, it's easy.
Why are there three
I
how?
solved it by myself.
I just told you there were going to be fractional coefficients.
Oh, no, fraction.
What's my
I tried it by myself.
Go back up for a second.
What's the matter?
I don't understand the last one. How'd you get negative, you added negative 24 plus 4.
I add those two numbers together. Hess's law of heat summation. So we're going to add the heats at the end to get the energy. How'd I cancel out what?
Like, it's like cross multiply.
Oh, easy.
I don't know.
If something is on the reactant and the product side, they cancel.
Why is it 2 and 2?
Because I only had 6 of them on the left and I had 8 of them on the right.
Subtracting them?
Yes, ma'am.
So it's not like, no, it is. You cancel out on both sides of the equal sign.
Oh, wait,
No.
I agree with both of you. I understand what you both are saying,
Okay.
but you subtract.
Okay.
Now can I scroll?
Yes.
Scrolling. Woo! Okay, so first thing I would start with is that B2O3 because that's the most complex molecule going on here. Plus, we've got H's and O's and H2O's going on all over the place. Also, here's one where your states of matter.
No.
You've got H2O gas in equation 1. You have H2O liquid in equation 3. So watch out. So let's all agree.
So that's your target.
Bottom one is my target.
Okay.
Oh, no, it's state changing too.
Is it?
Oh, my God.
Dude, you are bringing it today. Can we all agree we're going to reverse the first equation to get that B2O3 over to the product side?
Yeah.
That's the most important thing we need to do. So that gives me B2H6 plus 3 O2s.
You have to write it in the states of matter.
I'm going to. B2O3, 3 H2Os. Those are gas. That's a solid. That's a gas. That's a gas. We reversed, so that became negative 2035 kilojoules. Okay. What's the next thing you would like to do?
Can we
Like
do
3
that?
halves oxygen,
I don't want to deal with oxygen till the very end.
then the B.
Let's deal with the B. The B makes more sense to me to deal with second because I've got 2B and I need 2B. So we can basically say, we've already used equation 1. Now let's just carry equation 2 down. And let's go 2 B's plus 3 H's 2's. It's making B2H6.
Because you're trying to make all of these turn out that.
Yes. We're trying to add these together to make them turn out to be that equation. And now we also have taken care of that B2H6. So now that cancels out quite nicely. We'll do that at the end. So now you've got 2 places to go next. You can either go to the O2 or the H2, or better yet, maybe both of them. No, not the H2O. I mean, you could do the H2O if you want.
You have to use every single thing though, right?
Probably. There aren't many of these where they're going to give you an extra reaction. What do you want to do? Which one? So she wants to multiply this. Whoopsie. You want to multiply that by 3. Good start.
No, that sounds right. Reverse it too? No, never mind.
See, do you have any H's in your target?
No.
Do you have any H's in your work that you need to cancel?
Yes.
Those are on the reactant side. So flip it. You want to R3 that.
But I thought oxygen needs to be on the reactant side.
You don't know that yet.
Oh, then the H2O is also.
So H2O liquid is right there now, and that's 3 H2O liquids is going to 3 H2 gases plus, just for Arian's sake, 3 halves O2.
Yeah.
And flip it, positive 286 times 3 is a positive 858. Last thing we've got to do, you have 3 H2O liquids and you have 3 H2O gases. We need to get rid of those H2O liquids.
Can you do 3?
So then
multiply by
you
3 halves?
reverse that one.
So reverse, whoopsie. So reverse that one. And how do I get a 2 to become a 3?
Times one.
Times 1. And so 3 times 2 is 6, divided by 2 is 3. So now I have 3 H2Os as a gas. I have 3 H2Os as a liquid. And positive 88 became negative 88 times 3 divided by 2, negative 132 kilojoules. Kilojoule. You laugh, but you'll be doing thermos and you will hear my voice in your head going kilojoule.
In the third one, how did we go to a reverse? Because I would have thought of the oxygen like it needs to be on the reactant side.
Because in reaction 3, I have a liquid and I need to get my liquid opposite. Also in reaction 1, I have a gas. I need to get my gases.
Okay.
So let's see what cancels now, kids.
So you look for canceling, not to form things.
Correct. I'm trying to get them to not form. So I just showed you my gases cancel my gases. Okay, now here's me. I'm attention to detail, unlike some people. I use different strikeouts to show what I'm canceling. So when I see horizontal line, I can find my horizontal lines. When I see forward hash, I can find forward hash, back hash and back hash. And you say, wait, you're going to run out of things,
Squiggly.
but I'm not. Now here's, we can squiggly, squiggly. Now the O2s. Fractions are very important, and so is math, arithmetic.
All right, I can do this.
Okay.
3/2 is
3/2 is 1.5. 3/2 goes bye-bye and 3 becomes 3/2. So now write down what you got. You've got 3/2 O2 plus 2 B's makes B2O3. I'm going to put states of matter on these, don't worry. Plus nothing.
plus nothing.
Yay. This isn't that bad. I kind of like this one. The other ones are a little bit like, I could cry, but these ones are just like,
Add up the heats and you get negative 1273.
I actually did that with my Casio.
they're fun. This one's fun.
These are a good way to finish this chapter.
Oh, this is it. No, we have Hess's law too. I thought, oh.
Well, but I mean,
need standard stuff.
yeah, we still have to do standards.
But this is like, nice.
Yeah, these are okay. Okay.
Are we doing the next one?
No, I don't have time to do that. So here's your answer. Delta H is negative 104.7 kilojoules.
Kilojoule.
Kilo?
How is this? Oh, never mind. It's the same thing. You just said about it. No, because I thought I was like, MC delta H reaction. I think like the MC delta.
Okay. Hess's law 2, same thing.
So when there's multiple equations, we use the Hess's law.
Yes, ma'am. It'll be very clear when you use Hess. That's the one good news. You know it's Hess when you see a bunch of different equations. We like that. Delta H here is positive 158. Kilojoule. Okay. Then the end of this is called standard enthalpies.
We're almost there.
If you like Hess, you're going to love standard enthalpies, although Aaron, you're going to have to do arithmetic. Okay, let's get through the definitions first. A standard state is the state of formation, a state of an element or a compound or a substance at room temperatures, which for thermodynamics are going to be defined as 1 atmosphere, 25 degrees Celsius, 1 atmosphere of a gas, and if it's a solution, it's going to be 1 molar. That's just what standard states are. Standard enthalpy change, delta H. Now, if you see that little degree sign, that means standard. And delta HF, we've already done. That's a heat of formation. When we were doing ionic compounds and doing lattice energies, heat of formation. That was the heat of that reaction. Keep in mind, for a pure element, it doesn't cost any energy to form it. And so enthalpy of formation is also called heat of formation. You will be given data tables. Data. Notice all the zeros. Super easy. Elements don't cost us any energy. To calculate it, products minus reactants. Keep that one until May. Because remember, we're doing delta H right now. We have another chapter of thermo where we have to do delta S and delta G. Products minus reactants.
So we're only doing delta H, not delta.
Correct. We're only doing H right now. So write a heat of formation for NaCl from their respective elements in their standard states. So what we're saying here is we want to form NaCl solid, and we want 1 mole of that. What is sodium in its standard state at room temperature?
Oh,
Sodium would be a solid. What about chlorine?
yeah.
Just a gas?
A liquid.
CO2.
Oh, it's like-
Diatomic.
It's 1/2 CO2.
I was going more for the Cl2 gas. But we don't need 2 of them. So put a 1/2.
It sounds kind of familiar, almost like the oswald process. Haber Bosch. Oh,
Haber-Bosch.
hey, which one was it? It's like the stupid thing.
Most things are solid, right?
Born-Haber.
Warren Haber, yeah.
What?
Most things are solid. Like, how do you know Na is a solid?
It's the metal.
Also, if you check it on water.
It's a metal. So use standard enthalpies of formation to calculate delta H. So I'm going to look on the chart and I'm going to write them underneath. So negative 45.9. These are going to be kilojoules per mole. Nothing. 91.3 and negative 241.8. Calculate it for the reaction. So
How did you get those numbers? Oh, from.
these are from a chart,
Oh, got it.
from reference. I'm reading the table for you. These are up in the table up above that I had circled. These are one of those, always start as far to the left as you can. I got 4 moles of NO times 91.3 kilojoules per mole. See where that 4? That's my coefficient. Plus 6 moles of water as a gas. Whoops. Times negative 241.8 kilojoules per mole. And that right there is products minus reactants. 4 moles of NH3 times negative 45.9 and 0, thank goodness. Delta H for this reaction boom.